So, hello everyone. Today is our final session of this weekly problem interaction session that you have been attending since last 13 weeks. So, uh, this today's session will mostly revolve or it will be oriented towards the problems will be that we have done in the course right from the beginning. So it will be like sort of we will be starting with the first chapter, and then as we move on we will be solving the MOSFET problems. So first we will start with the wave function problems that we had seen how this wave function, which was one of the fundamental quantities that we obtained from the equation, Schrodinger's equation, and then how we deduced that we can obtain the energy band diagrams, and how these potential profiles enable us to get different kind of EK relations. Okay, so today, what we will start with the problems that we have been dealing all throughout this course. So let's start. Okay. So it says that we have to consider the five plots as a case of for a particle in infinite potential well problem. Okay. So we have to comment about the graphs which are, wait a second. Okay, it's recording. Okay, I guess it's okay, it's recording. Okay, so the graphs over here shown in this what we can say in this problem says that we have to look and validate whether the graphs in the problem in the graph A and D, A is this, D is this is B, this is C, this is E. A and D violate the properties. Okay, so basically what we are into, we know that there are certain properties that are associated with the psi, the wave function. So one among them is this: psi has to be continuous and its derivative has to be continuous, and also it has to be normalizable between the limits minus infinity to infinity, so that there is some finite probability of finding the wave in between the region of the space that we are looking into. Okay, so basically clearly this A and this D, they are both continuous and their derivatives will also be continuous. So we can easily say that they do not violate any properties, while for the rest you can see that there will be these problems of the derivatives of the first derivative likewise. So they violate the properties of the wave function that are required for a particular wave function to be physically realizable. So this is some basic brush up about the wave function. So we needed this wave function to be continuous, its derivative to be continuous, and also we needed this wave function to be normalizable. Okay, now moving on towards the another concept which was associated with this actually which was associated with the lattice vectors, and then we saw that how this silicon lattice, they are basically two interpenetrating FCC lattices. Okay, but in that we had just seen the FCC lattice, the BCC lattice, or the simple cubic. We had not gone into the depth of these hexagonal lattices. So basically, what we will be doing over here is we will be simply proving this problem statement that the reciprocal lattice of a hexagonal Bravais lattice is also hexagonal. First of all, what is this hexagonal this lattice look like? Let me draw the hexagonal lattice first. So if this is the hexagon, okay, and it will be somewhat like this, it will be somewhat like this. Let me draw everything in solid. Okay, so this is, let us keep it like this. Okay, so the vectors, the lattice vectors are simply, if this is our z, okay, this is our z axis, this is our x, and let me keep this as y. Okay, so this is our y. My drawing might not be clear, I am sorry for that, but uh, this is what it should look like. So the vector a is in this direction along this a1. Okay, this is our vector a1. So this is our another vector which is a2, which will be some combination of x and y axis, and let this be the height of this hexagonal system, which is c. Let's denote it by c. Let's denote the side of this hexagonal system by some quantity. Let us say the size, each size is equal to a. Okay, this side is equal to a. The height we have found out, the side we have found out, and the vectors a1, a2, and a3 will be in the z direction. Okay, so we have this lattice vector representation for this hexagonal system. So what we have represented this vector a1 simply by the side a times the this unit vector along the x. Okay, so the a2 will simply be the this combination of these two, the one component along the x-axis and another component along the z-axis. So it, sorry, along the y-axis, it will be simply, let us skip minus, let's keep it plus, because plus is also valid as such, and then this will be root 3 by 2, okay, times the y hat. Okay, similarly the third vector a3 is simply c times z. Okay, let me keep it as c times z hat, and let me denote these vectors by simply by a, vector a, vector b, and vector c. Okay, this is the simple representation for these. Now we know the reciprocal lattice vector will simply be given by 2 pi times b cross c divided by the A dot B cross C. This is simple. Okay, we know that now. It is simple mathematics that we need to deal with. So this B cross C is simply, if I write these unit vectors, this is B is A by 2 and root 3 by 2. It's 0, it's 0, 0, and it's C1. Okay, as simple as it gets. Now from this we can say it's x hat root 3 by 2. So it has A with it as well. A times C1 minus times y hat will be having just A by 2 C1. Okay, for the z hat we will be having 0. The component of this thing will be 0. Now simply A dot B cross C will simply given by the value, which is A x dot root 3 by 2 A times C1. Sorry, this has to be like this, times this x hat, okay, minus times y hat A times C1 by 2. Okay, when I do the dot product, we know it has to be with the this dot product between the uh, x and y unit vectors will be 0, since they are perpendicular to each other, and between the x and x it will be simply 1. Okay, so it would be, we will be left with root 3 by 2 A times C1, and A times A will give us A square. So this is our A dot B cross C. Now this vector A is simply now the this B cross C 2 pi times B cross C, which is root 3 by 2 A times C1 x hat minus this A times C1 by 2 y hat divided by root 3 by 2 A square C. Or simply, let us do simple manipulations to this, and we can simply say this A square is simply equal to 2 pi by A. Okay, let's take this A by C1 to be as common, so that this A by C1 will cancel with this another A C1. So it is root 3 by 2 x hat minus 1 by 2. Okay, minus 1 by 2 y hat divided by root 3 by 2, or A vector reciprocal vector A will simply be x hat minus y hat by root 3. Now for the rest of the vectors, the reciprocal lattice vectors, we need to find the B and C now. So this vector B will simply be given by 2 pi C cross A divided by A dot B cross C. Okay, so C cross A is simply x hat, y hat, z hat. What is it? C cross A. Okay, C means 0, 0 and C1. A means simply uh, this A. What is it? A was our A times x hat and 0 0. Okay, so this means that for x I will be having 0 in the x component. For y I will be having a times c1 y hat. Okay, for z I will be having again 0. Okay, so this is the component c cross a. Okay, simple as it gets. So b is simply vector b is simply 2 pi a times c1 y hat by what was it? What was the volume? It is 3 root 3 by 2 a square c1 root 3 by 2 a sorry a2 not it, it's a square, it's not a2, a square c1. So this c1 will go, this will go, this will be simply 2 pi by a. It would simply be 2 pi by a into 2 by root 3, okay, y hat. So this is our vector, reciprocal vector b. Now what about the others? What about the other vectors? Now we have just one vector left, which is vector c. So this reciprocal lattice vector c is simply 2 pi times a cross b divided by a dot b cross c. Okay, so a cross b, we require this thing first. So x hat, y hat, z hat. A was a 0 0 and this b vector was a by 2 root 3 by 2 a 0. Okay, so what would it give us? For the x vector, for the x unit vector along x, we will be having 0. Okay, for y we will also be having 0. However, for z unit vector along z, we'll be having this to be equal to root 3 by 2 a square. Okay, yes, absolutely. Now this vector c is simply 2 pi a cross b is this root 3 by 2 a square z hat divided by the this a dot b cross c, which is root 3 by 2 a square by c1. Okay, so what it would result, this will cancel out, this will cancel out, and we will be left with simply 2 pi by c1 times the z hat. Okay, this is the value for this vector c, reciprocal lattice vector c. Now you can clearly see we have found out the reciprocal lattice vectors along the a, b and c. So these a, b and c we have found out along the x, y and z. Now we need to look into the its the angles between the all these lattice components that we have found out. For example, this lattice vector a dot b, which we will use to find out the angle between the lattice vector, this reciprocal lattice vector a and reciprocal lattice vector b. Okay, so it means that we have to calculate the a dot b. So a vector was this thing and b vector is this thing. A is 2 pi by a, simply it was x hat minus 1 by root 3 y hat, and b is simply, let me check, 2 pi by a. Okay, 2 pi by a, 2 by root 3 y hat. So it would be simply, this would simply be 2 pi by a whole squared. It will be minus 2 by 3 y. Okay, so this is this a dot b value that we have obtained. Now from this we know the a dot b is simply the dot product between two vectors is simply the magnitude of vector a and magnitude of vector b times the cos of the angle between both of these vectors. Oh, okay. So it means that we need to find out the magnitude of the vector A, which is simply this 2 pi by A will come out and it would be simply 1 square plus, I guess it was 1 by root 3. Yes, it will be 1 by 3. Okay, so it will be simply 2 pi by A times 2 by root 3. So this is the magnitude of vector A, and the magnitude of vector B will simply be this. This will simply be 2 pi by this thing 2 by root 3. Okay, so this A dot B is simply now A dot B is 2 pi by A. Okay, what was it? A dot B came out to be equal to 2 pi by A whole squared, okay, into minus 2 by 3 y hat. Okay, minus 2 by 3 y. Oh, why should it be y hat? It was the dot product. So minus 2 by 3. Okay, so it is 2 pi by a whole square minus 2 by 3. Magnitude of a is simply 2 pi by a times 2 by root 3, and magnitude of b is simply 2 pi by a into 2 by root 3 times this cos theta. This 2 pi by a, 2 pi by a will go. This is, what is it? It is simply this root 3 will go with this 3, 1 2 will go with another 2, and we will be simply left with cos theta is equal to minus 1 by 2, or theta is equal to cos inverse of minus 1 by 2, or simply theta is equal to 120 degrees. Okay, so the angle between the vectors A and B is simply 120. Angle between, vector A and vector B is 120. Similarly, for this A dot C, we can similarly say that A dot C is simply equal to 2 pi by A x hat minus 1 by root 3 y hat. C is simply along the z, z 2 pi by C1. So this clearly means that we have this dot product between the two to the perpendicular components. Okay, so it would simply be equal to 0. Okay, so it would simply be equal to 0, and it means that we have this value, this the angle between these components, which is this A and C, is simply because it is equal to 0, so it is simply 90 degrees. So angle between A and C reciprocal its vectors is 90 degrees. Okay, similarly, for this B dot C, which is simply this 2 pi by a 2 by root 3, I guess, along the y hat. Let us check the vector. Yes, it is this thing, 2 by a 2 by root 3 along y, and this c is simply 2 pi by c1 along z. Okay, 2 pi by c1 along z. So this is also equal to 0. Therefore, angle between B and C is 90 degrees. Okay, so from this, uh, clearly this magnitude for this is also for this a vector and b vector, they both were equal, as is evident from this. This is the magnitude for the vector a, this is the magnitude for the vector b. Both are equal, and they are not equal to the magnitude of the vector c1 c, and also the angles between the vector a and the reciprocal lattice vector b is 120 degree. So what have we found out? We have found out the reciprocal lattice of a hexagonal Bravais lattice is also hexagonal. So it is also hexagonal. As simple as it gets. Now moving towards another problem, which is associated, I guess, with the mass or the EK relation, whatever you would like to say. So it is, which of the following statements explains the relevance of effective mass being negative for some particles in solid state physics? Okay, so so it means that we have to first look into the concept of the effective mass that we have been dealing all throughout the course. Wait a second, we have some water, and then we will start this problem. Okay, so what we have been dealing with throughout this course is we want the this whatever we can say this, how does this electron move or how does it behave inside this crystal. Okay, whenever we have this periodic arrangement of the atoms, we need to find out how is this electron behaving, or how is the carrier, which is our mode of, or the which is our medium of transport in the devices, how does it move inside these crystals. So we have already seen whether this there are the energy band values, these allowed energy band values, and how this energy band structures can help us to obtain the all the relevant informations that we require about any system. So we have said that these energy band solutions, they can help us to obtain these allowed energy values and these momentum relations as well inside this, for example, inside any semiconductor crystal. So, but uh, uh, it has some lacking information about this. What we can say, what are the external conditions, like what, for example, we can say that uh, uh, we are not trying to determine anything, that how this time will evolve, how when this time evolves, how does the system will change. So we have to, okay, so we have to see whether there is certain quantity which is associated with this energy band structure that will help us to obtain the information regarding this system. So basically, you must have also gone through the Heisenberg's uncertainty principle relation, etc., and you must have seen that how the two quantities, these momentum and the position, they cannot be determined simultaneously. So in these quantum mechanics, we basically and mostly talk about the wave packets. Okay, we say that this basically these wave packets, we need to address, for example, because we are more oriented towards the classical mechanics. That's what we have been going through since the childhood. Sorry, not since the childhood, or we can say since the eighth or seventh standards of ours. So we have to we have this conceptualization of these classical mechanics. So if we are trying to find some analogy to that, it would really help us. So basically, the motion of these particles inside the crystal, we have to deal with something called the wave packets. Okay, we have to deal with something called the wave packets. Basically, what are these wave packets? So these are somewhat what we can say related to the classical particles, which are basically which these classical particles which are localized in a particular space. So what does this wave packet mean? Wave packet simply means, literally, it means that, wait a second. So it simply means that we have some packet of waves. It simply means that. Oh. So basically, it consists of there's these constant energy wave function solutions, which are closely grouped about some particular central energy value. Okay, these wave functions are taken to be such that we have this combination, that the probability of this particle is always the unity within this specified time. Okay, or we can say that we need to find out the this time evolution of this wave packet motion, because when we are applying some external agents, like we are applying some forces, we need to find out how does this electron behave in a crystal. So the motion of these wave particles to these external forces and its evolution with the time would be somewhat it would be somewhat analogous to the equation of motions, like sort. Okay, although it would not be correctly that classical equations, but it would somewhat give us idea that how these wave packets, uh, or these combinations, which are these are basically the combinations, rather I would say linear combinations of constant energy wave function solutions. Okay, wave function solutions, uh, which are uh, closely, rather grouped about the center energy. Okay, so we want to find the evolution of with these wave packets with the time, and how does these behave with the external agents. So you must be aware of the concept of this something called the center of mass of these classical particles. So we say that this center of mass moves with some velocity v. You must have seen that billiard ball example as well. So these, we can say that these classically, we are trying to classically compare our wave packets, so that we get the classical analogy of our these quantum wave, what we can say, quantum mechanical system. And we can say that these wave packets, we can consider them moving with some velocity, which we call by the name of this. We say that these wave packets, sorry, these wave packets center, similar to the center of the mass of any classical system, moves with a group velocity, which is some Vg, which will simply be the change in the this position with respect to the time. So they for example, if these are since these are the wave packets, they will be traveling with some frequency, which will be having some this wave number associated with it. So the basically this dispersion relation will give us this velocity, this group velocity will simply be equal to d omega by dk. Okay, so if we consider this free particle and a traveling wave sort of a thing, we will see that this group velocity has this relation with this, simply with this, what we can say, the energy. We say we know that E is h bar omega, and if we put this relation over here, we can say that it would simply be 1 by h bar d E by dk. Okay, it is as simple as that. This is the energy dispersion relation derivative. So these can be interpreted as the center values of these, what we can say, the energy and the center value of the momentum of this wave packet. Okay, this these are really quantities that would help us to determine the evolution of these wave packets. So moving forward, we can say that these now these wave packets, when we apply some external force to this wave packet, like I am applying the field to it. Okay, if I am applying some field to the wave packet, we will be having this, since we know that these crystalline forces are already taken account into the Schrodinger's equation when we have solved this. So we need to now take into account this external field, or the dopant atom, sorry, or the dopant atoms that might be present in the crystal. So in order to account for the external agents, we say that some force F is acting on this wave, this quantum mechanical system, and this will simply do some work, and as a result of this thing, we will be having the energy increment. So this energy increment, so simply this energy increment due to external force. Okay, so this energy increment will simply be due to the external force F dot dx, which is simply this force was simply, this dx is simply F forces as it is, v time vg is the group velocity, vg times dt. Okay, we can say that this force, or this group velocity extra, and once we will go through all the steps, we will have some relation between the force and the group velocity. It would be somewhat like this. We will be getting it F times mass times dvg by dt. Okay, this is similar to the what we have seen, F equal to ma, force is mass times the acceleration. But here this this is the acceleration kind of, this is the derivative of the group velocity. Okay, so it is the analogous to F equal to ma that we have seen for classical mechanical systems. So this m star will simply be equal to 1 by h bar square d square e by dk square. Okay, this is m star. So this effective mass or this m star, what we have been dealing with, is somewhat it is this actual mass in this system which has been replaced with this effective mass. So this effective mass basically implies that the motion of this motion of these electrons in a crystal can be described in this quasi classical manner or sort of a thing. Okay, so now we have this effective mass thing, and this effective mass thing, they that it just tries to show us the importance of the energy dispersion relation, because this ek is the energy dispersion relation. So this effective mass just tells us how important it is to analyze the energy band structures properly. So this basically this effective mass now, it is simply the quantity that will allow us to obtain all the related information regarding the particular wave packet's motion. Okay, so this effective mass is really important to us. So now the problem basically was, what does the relevance of effective mass? Okay, now what is the relevance of effective mass? We have seen that it would help us to obtain the evolution of these wave packets, which is basically the motion of our carriers in the system. So now what is the relevance of these effective mass being negative for some solid, for some particles in this solid state physics? So what does this mean? It simply means that they this this negative effective mass, it simply means, let me write this point, negative effective mass, it simply means that they when we have applied some external force, the electrons the electrons will the electrons will accelerate accelerate in the opposite in opposite direction. Okay, that is simply expected from the classical conditions. So this is in response to external forces. So it is simply that this negative effective mass, it simply means that we are having the opposite impact. Okay, so it says that an effective mass being negative indicates that the particle's behavior is unconventional and deviates from standard, which is cross. The phenomenon of negative effective mass is still a subject of ongoing research. False. Negative effective mass implies that the particle experiences attractive force towards the regions of higher potential, leading to unique electronic behavior. This is absolutely what we meant. Since this time evolution was given by this, or the external force evolution was given by this effective mass, and the electrons will attract in opposite direction. What does this statement tell us? It tells us that they, for example, when we are having this uh, electron attracted to, for example, the negative, for example, when we apply some bias, let's say it moved from the high potential to the low potential, and these holes or these negative effective mass, which is known by the name of the holes as well, implies that these they will attract, they will be attracted towards now the higher potential. Okay, so this is what it means, that the behavior of these negative effective mass particles will be opposite to that of the conventional particles that we have been dealing with. So these negative effective mass particles are also called holes, and they behave like they are acting opposite in to that of the electrons. Okay, opposing behavior to that of the electrons, so they will move, they will be attracted towards the higher potentials. Now, this is the same effective mass problem that we have been dealing with. This effective mass, as I have been telling, is actually very vast concept and requires to be understood properly. So it says that we have this energy dispersion relationship for a charge carrier system in a periodic crystal, and it is given by Ek equal 2 times sine square k. Okay, so we know that effective mass is simply h bar square d square E by dk square. Simply the derivative of this energy dispersion relation. From this, we know the Ek relation is this. We know this, the dE by dk is equal to d by dk of this 2 times sine square k, which is simply 2 times into 2 sine k into cos k, or 2 times sine 2k. 2 times sine theta cos theta is sine 2 theta. Okay, I have just used sine 2 theta is equal to 2 times sine theta cos theta. Okay, now d square E by dk square is simply equal to, it would simply be equal to 4 times cos of 2k. Okay, now let's substitute this in equation 1. M star will simply be equal to h bar square by 4 times cos of 2k. Okay, so which option does it resemble with? It resembles with the option, okay, option B. Now moving towards the from let's deviate from the conventional energy band structures or the conventional energy band what we have been dealing with. Now let's move towards the uh, carriers. How do we quantify these carriers in terms of the energy relations that we have been obtaining till now? So we have been obtaining these energy concentration relations, and these energy concentration relations are in terms of the, sorry, these carrier concentration relations are in terms of the energy. So this problem says that this semiconductor is having an intrinsic carrier concentration of 10 to the power of 10 cubic centimeter, and is doped with 10 to the power of 15 donor dopants. We have to, after doping, the Fermi level is located at some position which is given by EF of 0, and the doped semiconductor is then illuminated or irradiated with the 10 to the power of 20 photons per second, such that each photon that is impinging on this semiconductor will result in the generation of the electron hole pairs. And during this illumination, the Fermi level of holes is located at EFP. The thermal voltage value is given. Minority carrier lifetime is given. We have to find out the value of the EF0 minus EFP. So the solution to this problem is simply, we have been given the intrinsic carrier concentration, which is 10 to the power of 10 cubic centimeter, We have been given the doping concentration, which is 10 to the power of 15 cubic centimeter, and we have been told that the intrinsic is doped with donor. Okay, so this is, since this is donor, the Fermi level will be above the intrinsic Fermi level. So if this is my intrinsic Fermi level, this will be my EF0. Okay, this will be my conduction band edge. This will be my valence band edge. Now, now let's mm, try to find out the whole concentration, which will simply be given by the law of mass action, which is Ni square by Nd, and is equal to 10 to the power of 10 whole square by 10 to the power of 15, which is 10 to the power of 5, simply centimeter cube. Now, the location between the distance between this EF0 minus the intrinsic Fermi level is simply kT times ln of this Nd by Ni. Okay, so it is simply 0.025 into ln of Nd is 10 to the power of 15 and I is 10 to the power of 10. So it means that we have to calculate this ln of 10 to the power of 5. Okay, ln of 10 to the power of 5. Wait a second, let me open the calculator. 10 to the power of 5 into 0.025, which comes out to be equal to 0.288. Since this is in energy, it will be electron volts. Okay, now what we have done, we have we have illuminated this doped semiconductor with the 10 to the power of 20 photons per second, and each will generate one electron hole pair. So the generation is 10 to the power of 20, okay, photons or electron hole pairs per second. So this generation is simply delta P by tau P. Minority carrier lifetime for these holes is 10 to the power of -6 second. So the addition or the increased this excess hole concentration will simply be generation times the minority carrier lifetime, which is 10 to the power of 20 into 10 to the power of -6, which is simply this value, which is 10 to the power of 14 centimeter cube. Now, this what is this hole concentration? Hole concentration now. This rather I should say resultant hole concentration. Resultant hole concentration is simply the original hole concentration plus this excess hole concentration. The original hole concentration which we found out was equal to 10 to the power of 5. Okay, it is 10 to the power of 5 plus 10 to the power of 14. Okay, which approximately is equal to 10 to the power of 14 cubic centimeter. So from this we can find out now the difference between the intrinsic Fermi level and the quasi Fermi level of the holes, which will simply be kT ln of Na by Ni. The Na value is approximately now equal to 10 to the power of 14. It would be 0.025 ln of 10 to the power of 14 divided by 10 to the power of 10. So it is ln of 4. 10 to the power of 4, sorry. Ln of, let me calculate it. Ln of 10 to the power of 4 is simply 9 point something into 0.025, which is 0.23 electron volts. Okay, so this is our equation 2. This is our equation 1. We need to find out the difference between the Fermi level, which was EF naught, and the quasi Fermi level, which is located at the EFP. So we need to find out EF naught minus EFP. Okay, we need to find out this value for the EF naught minus EFP. So if we add these two equations, add adding equation 1 and 2, what we would get is we will be simply left with, let us add this thing first, EF naught minus EFI, EF naught minus EFI plus, okay, uh, EFI minus EFP, I minus EFP is simply equal to addition of these two, which is 0.23 and 0.288. It is 0.288 plus 0.23. So this EFI will go with this thing. We will simply get the difference of this EF0 and this EFP, which is simply equal to 0.518 electron volts. So we found out the difference between these two Fermi levels. Now moving towards another problem. This was simply the problem related to the excess carrier generation. Now the another problem that we will be dealing with is associated with the metal semiconductor Schottky contact. So MS contacts that we have been dealing with. This problem is associated with that concept only. So it says that we have some n-doped semiconductor which is having this doping concentration which varies. Sorry, okay. So which varies with this position given by this exponential decaying relation and naught times exponential of minus ax. Okay, the junction of the metal contact is located at x equal to 0 and the depletion region extends up to 2 by a, and the semiconductor permittivity has some permittivity which is given by Es. Q is the magnitude of charge. Assuming this full depletion approximation, this is really important, and the magnitude of built-in potential can be expressed. So we need to find out the value of this A in this problem. So uh, first of all, since we have this charge dopant concentration, from this whatever is the methodology that we have been following, which was solving this Poisson's equation, we will go with that thing only, because uh, had it been some conventional constant doping for which we knew this built-in potential relation, we would have easily said that this is the relation and this will be the value of, for example, built-in potential. But since this is the charge concentration, we have not seen it till now because it is of the form of exponential decaying. So it is some exponential of minus ax, okay, per cubic centimeter. Let's be careful about the units. And the depletion width, it extends, depletion width is equal to 2 by a, okay, whereas a is some constant. Now let me use first the Gauss law, which says that since this is a 1D problem, dE by dx will simply be rho by epsilon s. Okay, epsilon s is the permittivity of this material. Or simply the electric field will simply be the integral of the charge density divided by this epsilon s value. Now the charge density will simply be this q times, which is the magnitude of the electronic charge, this n naught minus ax dx integral divided by epsilon s. As simple as it gets. So now if I integrate it, it would simply be q times n naught exponential of minus ax divided by minus a. Okay, plus some constant. This is the thing with we have. Now to find out this constant, what we can do is we can clearly see that at the edge of this depletion region the electric field must vanish. So we would say we have used the full depletion approximation, and we would say clearly that this at x equal to this 2 by a, electric field has to be equal to 0. So it means that this electric field is equal to 0 at q by this will be n naught times minus 2. Okay, so this will simply be minus q times n naught by epsilon s a e to the power of minus a by 2 by a plus c. Okay, or simply c is equal to q times n naught epsilon s a e to the power of minus 2. Okay, so the electric field is simply equal to, let me check once again, electric field is simply equal to the summation of these two, which will be simply, let's take this minus q and not by a common. This, okay, it should also have this epsilon s. Sorry, it should also have the epsilon s in the denominator. So let's take it common, this q and not epsilon s by minus a. So it would simply q and not minus epsilon s a. I have taken it common is equal to exponential of minus ax. And this thing is plus, so it would be minus exponential of minus 2. So let us check. Yes, it is correct. Okay. So this is the relation for the electric field. Now we have to go to this Poisson's equation. We know that the derivative of the potential is simply the electric field, and electric field is given to us. So we can say this d phi by dx is simply minus and minus, this minus and this minus will go, and this d phi by dx will simply be q times n naught epsilon s a e to the power of minus ax minus e to the power of minus 2. So now let's solve for this. Let's solve for this phi. So this phi will simply be equal to q times n naught by epsilon s a, the integral of e to the power of minus ax minus e to the power of minus ax minus e to the power minus 2 dx. Okay, as simple as it gets. So now let's take the solution for this. It is simply q times n naught epsilon s a e to the power of minus ax divided by minus a, okay, minus times e to the power of minus 2 x plus c. Okay, now this built-in potential will simply be the potential difference between the value which will be at the depletion width 2 by a and at the semiconductor metal semiconductor junction. Please explain assignment 5 question number 2. Assignment 5, question number. Assignment 5, question number 2. Can you please share the question? Assignment 5, question number 2. Because if I open the, for example, this our course over here, it will get recorded and I will upload the video on the YouTube, and it would just show all the contents live there. So I don't want to do that. uh, okay, you can email me as well. My email address is ateeb20 at iitk.ac.in. Okay, so let's solve for this problem first. Okay, I don't know what question number it is and which assignment it is, but this is from the this year's assignments. All of these problems are from today's, all of the problems are from this year's assignment. And these are in mixed mode sort of a thing. We are doing this in a mixed kind of a thing. So this phi, what where were okay, if this we were looking for this built-in potential, we said that it would simply now the difference between the potential value at the depletion region and the metal semiconductor interface. This is the metal semiconductor interface and this is the depletion width xt. Okay, this is at xt. So it simply means we have to substitute these values in this phi, and the c and c will go because this is constant term. When we will put it in this, we will simply get q times n naught by epsilon sa. It would be simply exponential of minus a by 2 by a minus a. This will be minus times e to the power of minus 2 by a. Okay, so this is minus times, and when I put it to be equal to 0, this x term will go and we will be left with e to the power of 0 will be 1, and it would be simply 1 by a. Okay, as simple as it gets. So this a will be gone with this thing. This is simply now, if I take this 1 by 8 to be common term, this is a square. This is now minus e2. Okay, this is minus e2 times 2 plus 1. Okay, or simply, uh, wait a second. So it means that it is simply equal to 1 minus 3 times e to the power minus 2. So let's solve for this on the calculator. It is now some simple mathematical calculation. So it is 1 minus this thing, which is simply equal to 0.593. Okay, times the number, which is q times n naught epsilon s a square. Okay, this is what we have found out, or look by just looking into this, we have found out this expression for this built-in potential. Now moving towards another problem, which says that we have uh, this MOS cap. Basically now we are moving from this metal semiconductor junction to the MOS capacitor, which will be a two-terminal device. Okay, so this we are moving now to this MOS cap. We say that with this MOS cap we have the CV relation for a particular MOS cap, and this MOS cap is constructed using a p-doped intrinsic concentration of this 10 to the power of 10, and the doping concentration is approximately equal to 10 to the power of 12, 14, sorry, not 12. The capacitance voltage curve for this MOS capacitor is shown in this, and the thermal voltage is 25 millivolts, and the permittivity of vacuum is this. So we have to find out the permittivity value for the semiconductor. Okay, we have to find out the relative permittivity value of the semiconductor that has been used to build this MOS capacitor. Okay, so simply now what we can do, we can look into this curve and we can say the value of the 2 picofarad will be correspond to the depletion region. Okay, sorry, not depletion region, it would be accumulation. Accumulation, and in accumulation we have just the COX capacitance. Okay, the oxide capacitance, this will correspond to the depletion region, and it will be the onset of the inversion region, the whatever you would like to say. And at this point we will be having both COX and C depletion capacitance. Okay, this will be the corresponding to the that value. So if this is zero point 0.1, this is zero point 0.2, then this value is zero point 0.3 picofarad. Okay, so this is zero point 0.3 picofarad. Now where was it? Okay, so if this is zero point 0.3 picofarad, we have found out Cox, and this will be the total capacitance at that particular what you can say gate bias value. So now we have this Cox is simply 2 picofarad, we found out, and the C effective at the onset of inversion is zero point 0.3 picofarad. Okay, so why shouldn't say onset of inversion, but let's be more, what we can say, let's not be more specific into this. And so let's say that now this is the effective capacitance particular to that value. So the effective capacitance will simply be given by, it is the series combination of the oxide capacitance and the depletion capacitance. Okay, so basically what we are required to find over here is the, since we required this semiconductor permittivity, relative permittivity value, for that we need to find out this C depletion first. So the C depletion will simply be given by, it will be simply given by what I can say, 2 into 0.3 picofarad divided by 2 minus 0.3, which is 0.6, divided by 1.7, which is 0.6 divided by 1.7. 1.7, which is 0.35 picofarad. It is 0.35 picofarad. Okay, so this is the depletion capacitance value, and we know that the depletion capacitance per unit area is simply given by Q times epsilon S N A by Q type 2 times this potential, surface potential. So for this case, we have to assume this psi s to be equal to phi f, the onset of inversion. This we can say that we can say this psi s is equal to 2, not 2 phi f, which will be the strong inversion. Let's say this is the, since this is the start of the inversion, you can say this psi s, the surface potential is building up, and it is equal to phi f. So it is the intrinsic, what we can say, it would simply be given by the kT times ln of the doping, which is accepted doping, the intrinsic, divided by the intrinsic concentration, its logarithm. So it will be 25 millivolts. It will be 25 into 10 raised to the power minus 3. Ln of what is the value of Na? It is 10 to the power of 14 and Ni is 10 to the power of 10. So it is ln of 10 to the power of 4. And what we had seen previously, we had calculated ln of this thing 10 to the power of 4, which was ln of 0.23. So it is 0.23 simply. It is simply equal to 0.23. Okay, volts. Then it should be kT by Q since we are dealing in voltages. Okay, that's why I have written it in 0.23. Okay, now moving towards this epsilon s value, how can we find out the area we need? Area is 100 into 100 micrometer. So the area is 10 to the power. Area is 100 micrometer square, or it is 10 to the power of minus 4 meter square, or it would be simply 10 to the power of minus 4 centimeter square. Okay, this is the area. Now the C depletion value was, we can see clearly say that this C depletion by epsilon A, we can square this thing. We can square this thing. It would simply be Q times epsilon S and A by 2 uh, phi F. Okay. Uh, yes. So it is okay. So it would simply be equal to. Okay. Yes. Yes. This is the only unknown over here. So it would simply be equal to C dep square divided by A square into this 2 times the phi F, which was 0.23, divided by the electronic charge, which is 1.6 into 10 to the power of minus 19, into this value. Doping was 10 to the power of 14, and this epsilon s is simply epsilon r times the epsilon naught. This C depletion was 0.35 picofarad. It is 0.35 into 10 to the power of minus 12 whole square. Area is 10 to the power of minus 4 whole square. And this whole thing, let us solve it. Let me write it once again. 0.2 into 0.23, 1.6 into 10 to the power of minus 19 into 10 to the power of 14 into epsilon r. Let's keep it as it is. It would be 8.85, I guess. It is 8.85 into 10 to the power of minus 14 into 10 to the power of minus 14. So it now becomes the mathematical problem that is simple calculations. So let me put it in the calculator. 0.35 square this 1.6 divided by 8.85, 4 minus this thing. So it comes out to be equal to 3.98 into 10 to the power minus 3 into 10 to the power. Okay, it comes out to be equal to, this epsilon r comes out to be equal to 3.98. Okay, this is the relative permittivity of this of the semiconductor. Okay, so it has the value approximately equal to 3.98. Okay, now moving towards another problem, which says that we have this is some designer. He wants that the capacitor, he wants to actually to discharge a capacitor, okay, in his PCB. So from the initial condition of 3 volt to 1 volt, and he proposes two different methods, and let's investigate both of them. Okay, one is the exponential discharge of this capacitor, which obviously will be through the resistor, and another is the linear discharge, and for that we will be needing some little bit knowledge about the MOSFET, what we have seen in the previous lecture. We had seen that how in this deep triode region this MOSFET will act as the resistor, and how we are going, if we are going to use it as an amplifier, that it is some current voltage controlled current source, how we will be biasing our MOSFET in this saturation region. For this amplification purposes, we required this MOSFET to be operated in the saturation region. We wanted it to behave as a voltage controlled current source, okay, which was the input voltage was given at the VGS, and we do not want the output voltage to control this output current. We wanted this control to be minimal, okay. So now for this we have to, okay, it is recommended to read the conditions in saturation, deep triode, cutoff, etc. For this exponential discharge, let's say I have given you a MOSFET with this mobility dash dash dash, and what is the value of the gate voltage which needs to be applied to this MOSFET. We have seen that this MOSFET when biased in this triode region. So solution for this is, for this since this is exponential decay, it corresponds to the resistor is required, and in deep triode region we have this MOSFET behaving as a resistor, and then simply the resistance will simply be given by the gate bias dependent voltage, which is mu n C ox W by L VGS minus VTH. VTH is the threshold voltage. Okay. From this we can find out the value for this resistor, which is mu n C ox. Mu n is 100, sorry, 1000. C ox is 0.5 into 10 to the power of minus 6 micro. W by L is 10, and this VGS minus VTH is VTH. Where is VTH? VTH is 1 volt. Okay, so it would be like this. 0.5 will go above, it will be 2. This will be 10 to the power of minus 3, 1, 2, 3. It will go with this thing. So it would be approximately, not approximately, it would be just 200 divided by VGS minus 1. So this is the value of the resistor that we require. Now we know that this discharge, the discharge in the capacitor with time will simply be equal to e to the power of minus t by tau, where tau is the RC, this time constant, which will be simply given by this value of the R and C. And V0 was simply, I guess it was 3 volts. Yes, it is 3 volts, and the V final is 1 volt. V final is 1 volt, and V0 is 3 volt. So let me keep it, 1 is equal to 3 times e to the power of minus t by RC. Okay, RC value, let's keep it as it is. Let me take the ln. It will be simply ln of 3 is simply equal to t by RC. Okay, let us say, or this R is simply equal to T by C times, okay, T by C times ln of 3. Okay, so now this R came out to be equal to 200 by VGS minus 1. 200 by VGS minus 1, and this what I can say is equal to uh, what it is equal to. It's equal to t should be given in this problem, which is 50 microsecond. It is 50 into 10 to the power of minus 6. C is also given, I guess. It is 1 microfarad, which is 10 to the power of minus 6 ln of 3. So VGS is simply, this will go with this thing, this will cancel out with this thing. So it is 20, it is 4, it is simply 4 times ln of 3 plus 1. So 4 times ln of 3, let me calculate this value. So let me calculate this value first. Ln of 3 into 4 plus 1 is 5.394. It's 5.394 volts. Okay, we have found out this value, which came out to be equal to 5.394. Now for the another part, what we require, let's check the another part. We require the linear discharge, and for the linear discharge we know that we will be requiring this thing to act as a what we can say, the MOSFET, we require the MOSFET to act as a current sink kind of a thing. So we want to bias it in the saturation region. So if I bias the MOSFET in saturation region, bias in saturation region, so it means that the current will simply be mu n by 2 C ox W by L VGS minus VTH whole square. Okay, so this current is simply the discharge in the capacitor, which is dVc by dt, or this dVc is this delta Vc by delta t. This delta Vc will simply be equal to 3 minus 1, and delta t is the time, which will be 1 millisecond. Okay, sorry, which will be 1 millisecond, 10 to the power of minus 3. And the capacitance value is simply equal to, wait a second, 1 micro. Okay, capacitance value is 1 micro. So it is simply this value, what we will be solving for. This equating these two currents, we can say this VGS minus VTH, let me take the square root as well, is equal to 10 to the power of minus 3 times 2. This is the value of this thing only, multiplied by 2 times, okay, divided by mu n C ox W by L, whole thing under the square root. So it will be simply 4 into 10 to the power of minus 3. Mu was 1000, I guess. Let me check. Oh yes, Cox is 0.5 into 10 to the power of minus 6. It is 0.5 into 10 to the power of minus 6, and W by L is simply 10. Simply 10. Okay, this whole thing under the square root. This is 10 to the power of minus 3. It will go with this thing, and this will also go. It will be 4 by, simply 4 by root of 4 by 5. Root of 4 by 5 is simply 0.8. Root of 0.8 is what it is. Let me check. Root of 0.8 is 0.894. So VGS minus VTH is 0.894, or VGS is simply, VTH was 1 volt, 1 plus 0.894, which is 1.894 volt. MOSFETs. Okay, so we have found out the VGS value for this particular problem. Now, moving towards another problem, which says that we have these two identical MOSFETs where, okay, can you please write your email ID? Sorry, ATEEP20. Okay, you can check the chat box. I have sent you I have sent one message, which is my email address. Okay, so let me check again. Yes, this is correct. So now we have this another problem which is associated with the MOSFETs, which says that we have these two identical MOSFETs which are connected in series. Okay, so what we are required to find, we have to find out the conditions about these M1 and M2. Okay, what is the condition that we require? These two identical MOSFETs, what are the biasing conditions, whether the M1 is biased in saturation, whether the M2 is biased in saturation, and somewhat like that. Okay, so we need to find out that those things only. Now let me let me first ask you people. Oh, okay, let me solve by myself first. There is no point in asking. Okay, so it says that we have to check whether both the MOSFETs are in saturation, whether one is in saturation, another is in some other mode of operations, kind of a thing. And let me go to this directly to this problem and let me solve, and let me take the first condition. Well, let me say that both the MOSFETs are in saturation. Okay, if I say that both the MOSFETs are in saturation, what does it mean? It means that uh, it means that first of all, both are in series. It implies the current in the MOSFET 1 is equal to the current in the MOSFET 2, and uh, we have to say that these both MOSFETs assume both are in series. Sorry, both are in saturation, not series. Both are in saturation. Now, if both are in saturation and both are identical, let us say that beta by 2 is the, for example, this parameter for the MOSFET 1, or we can say, let me say it is like this, it is mu n C aux by 2 W by L VGS1 VGS1 minus VTH whole square is equal to mu n. I am writing mu n Cox by 2 W by L. They both are same because they are identical. So this will cancel out. Okay. So this times VGS2 minus VTH whole square. VGS1 is 3 minus Vx. Okay. Minus VTH whole square. VGS2 is VGS2 is 3 minus 0. 3 minus VTH whole square. Okay. These two equations can be equal only if and only if Vx is equal to 0. Okay. So if Vx is 0, what does it imply? It would mean that the VDS bias for this MOSFET, this drain to source bias, which is VDS2 is equal to Vx minus 0 is equal to 0, because now Vx is 0. It would mean that VDS is less than VGS2 minus VTH. 3 minus VTH, because this is 3, this will be some number, let us say it is 1 volt. So it would mean that 0 is less than 2, which would mean that the MOSFET is not in saturation, not in saturation. So this statement is wrong. Now there is another take, we need to take another what you can say condition and check whether the MOSFET is it is biased in the, it says that the both are biased in the linear region. Okay, if both are biased now in linear region, what does it imply? It means that this thing, uh, this, let me check for the first MOSFET. First MOSFET, VDS is, VDS1 is 5 minus Vx. Okay, and VGS1 is 3 minus Vx. Okay, 3 minus Vx, and let me take this Vt to be equal to 1 volt. So VGS1 minus VTH, rather let's write VTH is 3 minus Vx minus 1, which is 2 minus Vx. Okay, clearly VDS1 is greater than VGS1 minus VTH, because 5 minus Vx will be greater than 2 minus Vx. So it implies that M1 is in saturation. So we are for sure now for one thing that this M1 is always in saturation, and M2 is now not in saturation, because we first found out that M2 cannot be in saturation. So the only thing now left out is that M2 is in linear region. And if you solve for the equations or the conditions by equating that this ID1 is in saturation and ID2 is in linear region, you will get some you will get some values for the ID1 and ID, yeah, sorry, this Vx and the VTH. So you will not get what you can say confused, or you will find out that the currents, both the currents are reasonable, and both the MOSFETs satisfy the conditions for the biases being the same, or the biases being what we have obtained. So so I guess we would select the option, M2 operates in linear region and M1 operates in saturation. We'll select the option D. So can you please unmute if you have some questions? Because there is one question, but I I think it's from the assignment. It is from assignment 5, question number 2. Let me try to open it on my phone. Assignment 5, and so that it does not appear on the screen, because the person, I'm sorry that I was late in seeing the message that it has you have to share the email address. So I am not able to find it in my email address. Let me check once again. Sorry. Okay, this is not an email address. So let me check this by myself on my phone. So it is assignment 5, question number 2. Assignment 5. Let me open the course website. So I am okay. Let me go to my courses. Go to the course. Assignment 5, question number 2. Question number 2. Assignment 5. Question number 2. Okay. Consider an MS Schottky junction. Let's say the doping profile varies as a function given by this thing. Okay. Assume a full depletion approximation. The ratio of the electric field in the what is of this form. Okay. Are you present in this conversation? Hello. Yes. Okay. So you want me to solve this? Okay. So you want me to solve this for this question number two. It states that this. Okay. It is simple. You just have to use the Gauss law. Let us just go into this problem. We have to find the electric fields, which will be the function of the position. Okay, so it would simply be this. We will be finding this and d. We have seen this kind of a problem dE by dx. Like it is similar to this case. It's similar to this case. Okay, this n of x is some function of the exponential. I guess what I have seen this problem, I guess, previously. Someone else had also asked me the same thing. I just there is some this sine px that is confusing everyone. I guess there should have been. It's my take. I don't actually know because I have not framed this question. But from whatever I can deduce, I would say that this doping profile should have been and not exponential of alpha x, because it's rather I wouldn't I don't have that much expertise in the fabrication, but I won't say that this kind of doping profile is possible if we have this sign of px associated with this thing. So I would say that it should be and not times alpha x, and not times exponential of alpha x. So if you try to solve it with that thing, I guess you will be able to find it properly. But I guess they have provided a solution for this as well. Let me check the solution. Uh, Moreover, I cannot guarantee. Okay, they have said we have to solve the Poisson's equation, which is as expected. So the Taylor expansion for this, they take the Taylor expansion for this by saying that one exponential of x is 1 plus x to the power. So they just take 1 plus x, and then they solve for this integral, I guess. And they say that x of t by 4 is sine of a times sine of b. So, frankly speaking, I have seen this question previously, but I have someone had asked me in the email, I guess, or somewhat like that. But this problem, for sure, this needs to be looked into. You must put this problem on the forum. You must tell them that you want detailed solution or the detailed explanation for this, because I myself am not sure about this problem. I have, what I can say, I actually have tried to solve with that sine px, but I was not able to get the solution, frankly speaking. So this problem I have actually seen previously. So what I would suggest you that please try to write on the forum, or because I have not framed these any of these questions, or this or not either the solutions I am framing. So the person who has framed this question might be able to answer it more perfectly, because if you try to put it on forum, the person who has put it on this website, which is our professor, the professor will talk to his student and he will try to elaborate you on this. But I am not myself sure on this problem. I have tried to solve it once, but I was not able to get its solution. I guess there is either there is something wrong in our understanding, because two or three students, I guess, talked about a similar problem and I myself was not able to do it. Either there is some major problem in our understanding, or there might be some typo in the question. There might be, I'm not sure. So if there is some other question which is associated with these assignments or anything, you can ask. But I guess about this problem, I don't think that I have the solution for this, because I guess there might be some typo in the problem. There might be. I'm not sure, because the doping profile also does not look realistic to me. It does not look realistic to me. Okay. So if okay, let me check the chat. Okay, so you have said okay to something. Okay, so it's fine. So if we have some other questions related to this, what we can say, coursework, or some other even non-technical questions, we can ask, because this will be our last session, and after this we will not be having any live sessions, and there will be, I guess, we will be having these examinations for the course. And I would like to thank all the students who have opted for this course and surely have benefited from the course, because this has been some vast course which professor has taught us beautifully, covering each aspect of the semiconductor device physics, right from the wave function kind of a thing and the quantum mechanics, and taking us down to the circuit level. This is really amazing that what he has taught us. He has just given us the everything that we require in the field of the device physics. Now it's up to our understanding and up to our efforts, how much efforts we put into this field, so that we get the deeper and deeper insights. Otherwise, the professor has given you each aspect that you require to excel in this course or excel in this field moving forward in the future. So if there are no questions, and
Sir,
okay,
uh,
okay,
sir, how will be the question pattern
for what?
for the final exam?
Ma'am, I'm actually really sorry, but I do not set any of the questions. I am just here to solve the assignment problems. I do not know anything about that.
Okay, sir.
There are other course TAs which might be knowing about this. Like we are two this online TAs which teach you the problems. We do not have any information regarding any of these things, like who sets up the questions or who how it is done. Most probably it will be done by the professor in a couple of for example, couple of weeks, or whenever your exam will be. He will just frame the questions and he will just put it online. I don't know how it will happen, but it is some other persons who do this
Okay,
kind of
sir.
a thing.
Okay.
Okay. So, Mr. Vinod, if you have some question, you can ask. Okay, Mr. Vinod has left. So, if there are no questions, Miss Parna, we can leave the you can leave the meeting, so I can end the session and recording for today's session. So, thank you everyone for joining this live interaction classes. Thank you once again.